Alright, let's dive into our really cool story of engineering magic. We're going to talk about how a powerful, kind of wild invention from the 1880s was taught a brilliant new trick, one that made it the absolute heart of our electric future. Let's get into it. It sounds kind of wild, right? But it's totally true. The powerhouse inside so many of the world's most advanced electric cars is a direct descendant of the three-phase AC induction motor, a design that goes all the way back to the one and only Nikola Tesla. It's a piece of history that is literally driving us forward. So getting from a 19th century patent to the sleek EVs we see today, well, that was a heck of a journey. It took over 100 years and a few key breakthroughs to make it happen. For decades after it was invented, this amazing motor was basically changed to a wall socket. It was an industrial workhorse, but it couldn't really go anywhere. Then, in the 1960s, digital electronics started to change the game. But the real game changer came in the 90s with the portable inverter. Say, that's the device that could finally take DC power from a battery and turn it into the AC power the motor needed to run. That's what made the first modern EVs possible. And fun fact, that check was eventually licensed by the founders of Tesla Motors. All the dots just connect. But here's the thing. Making the motor portable, that was only half the battle. Its raw power was never in doubt, but actually controlling that power with any kind of precision. Oh, that was a whole other massive challenge. And you can see why engineers were so obsessed with cracking this puzzle. I mean, this motor is a beast. It's incredibly powerful, it's super reliable, and it's everywhere. The problem wasn't its strength, it was its stubbornness. It was like having a champion racehorse that you just couldn't steer. Okay? So here's the root of the problem. Controlling a simple DC motor, it's a piece of cake. Imagine you have two separate knobs on the control panel. One controls the power or torque, the other controls the magnetic field or flux. Simple, you can tweak one without messing up the other. But with an AC induction motor, it's like those two knobs are welded together. You try to turn up the torque and you accidentally mess with the flux. This coupling, as they call it, makes precise, responsive control a total nightmare. So that became the mission, right? The holy grail for engineers was achieving what they called decoupling. They needed to find a way to mathematically pry those two knobs apart, to untangle those controls, and give this powerful AC motor the same simple precision as a DC motor. But how on earth could they do that? Well, the answer wasn't found in new gear or a new piece of hardware. Nope, this solution was pure software. An incredibly elegant, mind-bending mathematical trick that completely changed the game. It's called Field-Oriented Control, or FOC for short, and you can think of it like a universal translator running on a tiny computer chip. It's the set of really complex calculations that creates a kind of digital illusion. It basically tricks the complex AC motor into behaving like a simple, predictable DC motor. It's genius. So, how does this magic trick actually work? Okay, first, the controller measures the three messy wavy AC currents coming from the motor. Then something called the Clarke transform steps in to simplify those three waves into just two. But here's the brilliant part, the pair transform. It mathematically rotates the point of view to perfectly match the motor's rotation, and by doing that, it transforms those two messy waves into two beautiful, simple, stable DC values. And boom, just like that, the problem is solved. In this new mathematical world, one of those DC values gives you direct control over torque, and the other gives you direct control over flux. We finally have our two independent knobs, decoupling achieved. Now, you have this brilliant mathematical idea, but you don't just go out and build a multi-million-dollar system and hope for the best, right? Not these days. Modern engineering happens in the virtual world first. So what you're looking at here, this isn't just a diagram. It's what we call a digital twin. It's a complete, working, living, breathing simulation of the motor, the power electronics, the whole shebang. This is the virtual sandbox where engineers get to play and perfect the system before a single screw gets turned in the real world. And inside this digital twin, every single piece has a job to do. You've got the virtual motor itself, of course. Then you've got the IFOC block. That's the brain, the part doing all that crazy math we talked about. The PI regulator acts like a supervisor, constantly checking for errors and making tiny corrections. The PWM and inverter blocks are the muscle, turning the brain's commands into high power voltage. And the AD blocks, those are the system's senses, feeding real-time info back to the brain. Okay, So we've got the problem, we've got the clever mod to solve it, and we've built a perfect digital copy to test it on. The only thing left to do now is press run. And this right here, this is the moment of truth for any big engineering project. Does the theory actually work in practice, even if it's a virtual practice? Can our algorithm really tame this wild beast of a model? The results are in, and they are absolutely stunning. The actual torque the virtual motor produces tracks the target command almost perfectly. I mean, look at that. And even when the simulation throws a wrench in the works, like a sudden heavy load that's like an EV hitting a super steep hill, the controller responds instantly. It maintains perfect control without even breaking a sweat. So the conclusion is crystal clear. In the digital world, at least, the challenge has been completely solved. The control algorithm is precise enough for incredible performance, stable enough for safety, and tough enough to handle anything the real world can throw at it. And look, this isn't just some cool academic exercise. This is the technology that makes modern electric cars feel so responsive and so efficient. It's the brain inside high-precision robots and automated factories. And by figuring all this out in a simulation first, companies save millions of dollars and tons of time getting better products out into the world faster. When you step back and look at it, this is just an amazing story about the power of software to completely redefine what hardware can do. It proves that even a 140-year-old invention isn't done learning. With the right code, you can teach it brilliant new tricks. And that just leaves you with one final thought, doesn't it? What are we going to teach the machines of tomorrow?